So here are your learning objectives. Here's your first definition. Definitely says slide 16. That's not correct. All right. So describe the surface S by the following. Okay, so to get an idea of the shape of the surface, we first plot some points. Since the parameter domain is all R2, we can choose any value for U and V and plot the corresponding points. So if U equals V equals 0, then you would have R0, which would be 1, 0, 0. So the point 1, 0, 0 is on S. Similarly, you would have R I, 2, and you would get the point out would be -1, 0, 2. And I guess I'll write in another color. And okay, so those three are all on S. Although plotting the points may give us an idea of the shape of the surface, we usually need quite a few points to see the shape. Since it is time consuming to plot dozens or hundreds of points, we use another strategy. To visualize S, we visualize two families of curves that lie on S. In the first family of curves, we would hold U constant, and in the second family, we would hold V constant. So if you need a little note for your families, I'm not talking about like a Merry Christmas card. You would hold U constant, and then hold V constant. Okay. This allows us to build a skeleton of the surface, thereby getting an idea of its shape. So first we want to suppose that U is the constant K, then the curve traced out by the parameterization. If you guys say that word better than me, I'm so proud of you. Cosine K sine K V, which gives a vertical line that goes through the point. There's a vertical line that goes through the point cosine K sine K V in the XY plane. All right, now suppose that V is the constant K. So you would have cosine U, sine U, K, which gives a circle in the plane Z. z equal to k, with r equal to 1 and a center at 0, 0, k. If u is held constant, then we get vertical lines. If v is held constant, then we get circles of radius 1 centered around the vertical line that goes through the origin. Therefore, the surface traced out by the parameterization is a cylinder x squared plus y squared. That just looks like a weird cartoon tongue. Equals 1. And now you can see what it looks like. Nope, don't want you to do that. Not really sure why this guy is not. Okay, there we go. There we go. All right, cool. So that's right. I had to, for this one, to like make it on the page, I had to do like a really weird. Oh, I stole it from the other Jamboard. That's what I did. Instead of recreating it, I just stole it from the other Jamboard. That's why it looks a little weird. But all right, you get the picture. All right, so that's you get the picture because it's a picture. Sorry, dad joking today. All right. Okay, so notice that if x equals cosine u, and y equals sine u, then x squared plus y squared equals 1. So the points from S do not lie on the cylinder. Conversely, each point on the cylinder is contained in some cosine u, sine u, k. For some k, therefore each point on the cylinder is contained in the parameterized surface. This one. That's why you couldn't see it till the end. But there it is for you. Is there anything there? No, I didn't think so. Okay. Let me get rid of that one. All right. This is why I split the why I split it up a little bit. Okay, so we want to describe a surface. Describe as parameterized by the following. Legit might be the hardest word in the math language for me. I don't know why. If someone wants to come up with a harder math word, just go for it. But all right, so notice that if u is held constant, then the resulting curve is a circle of radius u in the plane z equals u squared. So if we hold u constant, then we would have a circle of radius u in the plane z equals u squared. Therefore, u increases, the radius of the resulting circle increases. If we hold v constant, then the resulting curve is a vertical parabola. Therefore, we expect the surface to be an elliptic paraboloid. To confirm this, we're going to do the following. So we expect the surface okay, so what we know then is x squared plus y squared equals u cosine v squared, excuse me, plus u sine v squared. So that means we have u squared cosine squared v plus u squared sine squared v. So that's just u squared, which is z. So therefore, the surface of the elliptic paraboloid is x squared plus y squared equals z. And we will show you the picture. There you go. Okay. Let's rock it. All right, so finding a parameterization given the cone laying on or above the plane z equals -2. So the horizontal cross section of the cone at height is a circle. X squared plus y squared equals u squared. We know that from what we just did. Therefore, a point on the cone at height u has the following coordinates. Almost went Christmas again. U cosine v, u sine v, u for angle v. Hence, a parameterization of the cone is r u v equals having a hard time with the writing right now. Since we are not interested in the entire cone, only the portion above the plane z equals -2, the parameter domain is given by -2 to u, infinity, and 0 being to pi. And we will show you the picture. There is the picture. Okay. All right, we have a set of notes, two definitions. All right, okay. So here's what we're looking at. Which of the following figures is smooth? I mean, obviously, I think you guys could figure out which one is smooth just by looking, but clearly we're going to work through it. So the first one for A, we would do the following. RUV sign U, and then sign B. And that's on 0 to U to pi, and then 0 to V to 2 pi. All right, so we can use technology to verify it. Notice that the vectors, so we're going to have R sub U and when it says technology, you guys can use Wolfram Alpha. There's a whole bunch of stuff on the internet. I doubt I have anything on your exam that would say use technology. Okay, and then we would have RV, not the one you drive around in. Uh, cosine. Exists for any choice of u and v in the parameter domain, and then we would have the following. This is a lot of writing. So you would have RU cross RV. So it's going to be what we just found, the minus 2 plus cosine V sine U. Obviously, my stuff's going to not be as nicely written as yours should be. 2 plus cosine U cosine V, and then 0. And then minus sine V cosine U minus sine V sine U, and then cosine V. All right. I am hoping at this point that you guys can handle that cross. Uh, hmm. I think I can put it in Jamboards whenever you're working with a study buddy, and especially if you guys are like maybe working not right next to each other. Jamboards are awesome. You can both work on them at the same time, and they're through Google, so they're free. Granted, I was just creating that myself, just on 2 different devices, but all right, so the k component of this vector is 0 if and only if v equals 0 or v equals pi. So k equals 0 if and only if v equals 0 or v equals pi. Then the only choices for u that make the j component 0 are zero or pi. But these choices of u do not make the I component 0. Therefore, R cross RU cross RV is not 0 for any of the choices UV in the parameter domain, and the parameterization is smooth. So, not equal to 0 for these U's. So, is smooth. Part A is smooth. Notice the corresponding surface has no sharp corners. In the pyramid, the sharpness of the corners ensures that the directional derivatives do not exist at these locations. Therefore, the pyramid has no smooth parameterization. However, the pyramid consists of 5 smooth faces, and thus this surface is piecewise smooth. You can't just say it's not smooth, it is piecewise smooth because of the faces. This is just straight up smooth. Okay. All right. We have a definition. All right. We're moving. Okay, so let's take a quick look. Calculate the lateral surface area, the area of the side, not including the base, of the right circular cone with height h and radius r. See, we have a little analysis down at the bottom. Oh, we did. A little analysis down at the bottom. Before calculating the surface area of the cone using equation 618 that we just had, we're going to use equation 618. We need a parameterization. We assume that the cone is in R cubed. With its vertex at the origin. Now I can show you the picture. There you go. Okay. To obtain a parameterization, let alpha be the angle that is swept out by starting at the positive z-axis and ending at the cone, and let this equal this. Hold on. So we have alpha which is this angle. Here it is, alpha. Oh, you see it then. They're both here. Okay. For the height value V with 0, so you can see it down here too. Here it is. Here's all the information right here. The radius of the circle formed by intersecting the cone with the plane Z equals V is kV. So radius is equal to kV. Therefore, we would have, and you see it down there, it's already given. KV cosine U, KV sine U, V. It's going to be from 0 to U to pi, and then 0 to V to H. The idea behind this parameterization is that for a fixed value V, the circle swept out by letting U vary is the circle at height V and radius kV. As V increases, the parameterization sweeps out a stack of circles, resulting in the desired cone. I revealed the image. Oh, I had no idea there was so much more to that. Oh, mercy. Okay. Don't know if I'm gonna have to. Man. That's what we're gonna do. I'm gonna show it to you. All right. Okay. So, you can see that we have TU and the parameterization of it and what TV is. So then we do TU cross TV. We do the cross. We find the magnitude. I'm gonna let you guys copy up to that point. Okay. And then I'm going to scroll a little bit more. So here's using equation 618, the surface area of the cone. Okay. So therefore the lateral area of the cone is the following. Yeah. That was just so much. All right, sorry, that one was just so long, and I knew if I tried to write it, we would run out of space. Okay, let's try this. Okay, so R cosine theta sine phi R sine theta, and then R. Okay. And then, oops. Okay, so the tangent vectors would be and if you guys are working this ahead of me, keep it going. Just make sure that you don't miss any steps. Okay, so when we do our cross, let me see, let me throw these in. All right, we have a little bit more left. So what you need to notice is that sine rho is going to be greater than or equal to 0 because this justifies the equation okay, so then the surface area of the sphere is I feel like most of you should have known where that was going to end. We have derived the familiar formula for the surface area of a sphere using surface integrals. Don't be surprised if I end up pulling in answers the way I just did for the rest of these.